We are going to look at molecular bonding in this video. Molecular bonding, we can get into polar and nonpolar, we can get into some diatomics, and then we're also going to deal with naming and formula writing. So molecular bonds are when two or more atoms will share their electrons. All of these happen with our nonmetals, or so those that are on the right side of the periodic table. We have two types. We have polar molecular bonds and we have nonpolar. So in the nonpolar, they're going to be sharing equally, and in the polar, we're going to see that those electrons kind of stay on one atom more than the other. All right, so we are going to look at this polar molecular compound first. In the polar molecular compound, one atom is going to hold on to those electrons a little bit more than the other. So we kind of see there's this slightly negative side, which gives us our polarities. So again, they're not shared equally. These electrons are going to hang out on one atom over the other. So if we look at our drawing here and we have this little electron, it is going to spend most of its time circling around this atom, and then it's going to maybe make a pass down here with the hydrogen. But most of its time it spends up on the chlorine. So we say that this one is slightly negative versus a slightly positive side. These aren't full charges. It's not like we have a negative side and a positive side. They are slightly more negative because the electron spends more time up there on one than the other. So just kind of a definitional sort of thing, we see that when electrons are pulled closer to one, it's called a dipole, or two poles on there. The end with the bond is slightly more negative, the end with the electron, and then the other one is slightly more positive. Really cool thing that happens with polar molecules, if we're going to put them in a magnetic field, so as you can see here we have these little magnetic plates, a negative and a positive side, we see that the particles themselves will align, so that way their positive end is pointing towards the negative plate and their negative end is pointing towards the positive plate. All right, so the next type of bonding is still a molecular bond, so still sharing of electrons, but this one is nonpolar. And so in this case, all of our electrons are shared equally. So the electron spends just as much time on one atom as it does on the other. So if we have a particle here and we have another particle over here, the electron is going to go just kind of back and forth and kind of share that time evenly with each. It does not have a dipole, so there's no polarity to this. There's no slightly positive, slightly negative. They are just very much neutral. So a very specific type of nonpolar molecular bonds involve the diatomics. We're going to be memorizing these. These elements only exist in pairs. So if we say oxygen gas, well, oxygen gas isn't O, just oxygen for O, it is O2, because when it's by itself, oxygen is going to pair with another oxygen. Whereas like if you see lithium or potassium or sodium, that would just be Li, K, or Na. Here with the diatomics, we see them being paired together. Di meaning two, atomics meaning atoms, so we have literally two atoms. All right, so naming molecular compounds has got to be like one of the easiest things that we are going to be doing. So with molecular compounds, we have to pay attention to the number of atoms for each element are listed, and we are going to use prefixes. These are on your periodic table. They'll be given to you on your assessments, but we have mono for 1, di for 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, and nona 9, and then deca for 10. So we're going to be using these repeatedly throughout the rest of the semester. All right, so for molecular compounds, we're not going to pay attention to the charges. We are only working with nonmetals. So for the most part, these only have, if they have a charge, it's going to be a negative charge. And since they both want those electrons so badly that they're going to have to end up sharing. Unlike the ionic compounds where one is like, okay, here you go, you can just have this, I'll be positive, and the other one's like, oh, thank you, I'll take it and be negative. In the molecular compounds, they both want them really, really bad, so they end up having to share. So so our charges are never going to balance. When you're naming, again, like we did with the first one, the last one gets changed to IDE. We're going to use the Greek prefixes that I showed you on the last slide, and we're not going to use mono for that first element. So if we're looking at CO, it's going to be carbon monoxide, not monocarbon monoxide. So here we have naming molecular compounds. So I've just kind of listed a few here. So in this first one, we have carbon with just one. So we're not going to say monocarbon, we're just going to say carbon. And then for oxygen, that would be oxide, because we're going to use that IDE ending on the second one. But with the 2, we're going to put a di in front of it. So this one is written as carbon dioxide. The next example that we have here, where we have N2O, that N goes with nitrogen, so we're just going to say nitrogen like normal, but we're going to put a di in front of it to represent the 2. And then oxide is by itself, so it's monoxide. Our next example is NO3, so N is by itself. We're going to use nitrogen because it's the first one listed instead of mononitrogen. Then for the oxygen, it has a 3, so we're going to say trioxide. So we have nitrogen trioxide. Our next example is SO2. So again, sulfur just having one element there, one atom. We're not going to use mono because it's the first. So it would just be sulfur, and then since there's 2 oxygens, we're going to use dioxide. So it's sulfur dioxide. In our last example, we have tetraphosphorus decaoxide. In our last example, we have P4O10, so the 4 would give us a tetra, and the 10 would give us a deca, so we have tetraphosphorus decoxide. Here we're going to look at writing the formulas, and these are super simple. You're just going to look at the word that's there and write its symbol. So for example, we have carbon, which is C. Then we have trichloride, so the word chloride is in there for Cl. Tri means 3, so we have 3 Cls. So our formula is CCl3. For dinitrogen pentoxide, we have nitrogen and oxide or oxygen. The di before nitrogen means 2. The pent before the oxide means 5. So we have N2O5. Trihydrogen monoxide. So the tri before the hydrogen is 3. The mono before the oxide is 1. So we have H3O1, but we ignore the 1. A di before phosphorus means we have 2, and a hept before sulfide means we have 7, so it's P2S7. And lastly, we have phosphorus with nothing before it, so that means just 1. And then we have tetraiodide, so tetra meaning 4, and iodide with an I, so we have PI4.